always point away from the sun. So what happens is that the comet comes in from somewhere out in the Oort cloud, and the sunlight warms up the comet, releasing the dust and the gas, and the sunlight pushes on the dust and the gas. So the tail streams behind the comet. And then when the comet comes around and goes back out, the sunlight is still pushing on it, and the tail streams in front of the comet. And Kepler realized that, and he guessed correctly that it was because of the push of the sunlight. And what we're going to do is we're going to use the pressure of light to push on our atoms to slow them down, and that is the idea of laser cooling. The idea of laser cooling is totally crazy. We all know that if you shine light on something, it gets hot. And what I'm claiming is we can shine light on something and it gets cold. And to understand that, you need to understand two things. One is the idea of resonance. The idea that light will only exert a force on an atom when the atom absorbs the light, and the atom will only absorb the light if the frequency of the light is just right. And it has to be really just right. Like, it has to be within a part in 100 million, or the atom will not absorb the light. That's one thing. The other thing we already talked about, the Doppler effect. If the atom is moving, it looks to the atom as if the frequency of the light is different. Higher if it's moving toward the source of the light, and lower if it's moving away. Now you know what you need to know in order to understand laser cooling. And as Wendell pointed out, the idea of laser cooling came in 1975 from Weinman and Daniel and Hensch and Shallow. And this was a really great idea, independently from these four people, all of whom eventually got a Nobel Prize for something else. So these people were really sharp. Okay, so here's the idea. Imagine a gas of atoms. Some of them are going to the left, some of them are going to the right. So imagine I'm this atom moving this direction toward this laser beam, which is tuned a little below the resonant frequency of the atom. Because I'm moving toward it, the frequency looks like it's higher, and that means it looks like it's the frequency I want to absorb. I absorb the light and slow down. But if I'm moving away from that light in this direction, then the light frequency appears to be shifted down, and I don't absorb it. You see, if I did, I would speed up, but I don't absorb it much. So I slow down a lot when I go this way, and I hardly speed up at all when I go this way. And now, if we bring in light from the other direction, then no matter which way the atom goes, it picks out the laser beam that is opposing its motion, absorbs it preferentially, and slows down. And it works just as well in 3 dimensions. And when Steve Chu did this in 1985 at Bell Labs, he realized that the atom felt as if it were in a viscous fluid. Because if you were in a swimming pool full of molasses, if you tried to move, there would be a force opposing your motion no matter which way you went. Well, the atom feels the same way, and so he called it optical molasses. And here's a picture of optical molasses from our lab. I'm not sure if you can see the laser beams coming in from this direction. They're intersecting here, and here's where the atoms feel this viscous force in all directions. This is about a centimeter across. There's about 100 million atoms here, and the question is, what is the temperature? We can calculate what the temperature is. I could go through that, but we don't have enough time. It's just a calculation of a few minutes. And you can calculate that the heating that comes from the random re-emission of the photons that the atom absorbs will heat the atoms, and this process, this Doppler process that I've talked about, will cool them, and they come to equilibrium. And the theory says that the temperature could be as low as 240 microkelvin. Well, the way Steve Chu measured the temperature was, he held the atoms here in the optical molasses, he turned the laser beams off, they sort of explode, expanding into the vacuum. The hotter they are, the faster they explode. Then he turns the laser beams on after a few thousandths of a second, and recaptures the atoms that are there, and by measuring the ratio of the number of atoms you start with to the number of atoms you end up with, you can calculate the temperature, which he did. And it was 240 microkelvin, the lowest temperature that the theory says is possible. This was wonderful. Everybody was so happy because this first experiment, everything worked perfectly. And we remeasured it, doing exactly the same thing that done. We got 240 microkelvin. And then other people measured it with different atoms, and they got what they expected. And then we started to do some more measurements, just to measure things like how sticky molasses was, and it didn't work at all. Something was terribly wrong. And so we decided to measure the temperature much, much more carefully. And unexpectedly, in 1988, we found out that the temperature was in fact much, much colder than had been predicted by theory. Now think about this. The whole idea of the experiment was to get the atoms as cold as we could. We had apparently gotten the atoms colder than we could. This is clearly a violation of Murphy's Law. And, physicists believe in Murphy's Law almost as much as we believe in conservation of energy. So this was kind of weird, and we had to have really good evidence for this. So we compiled some really good evidence. And because, we felt like these poor devils in this cartoon who have seen something that's a whole lot colder than it's supposed to be for the environment they're in. But we confirmed that it was indeed that cold. And then there were a lot of heated discussions about what kind of a theory was going to replace the old theory. And I wish I had time to tell you about the nature of the new theory. Eventually, a new theory emerged from Claude Cohn-Tanucci and his young colleague Jean Balibar in Paris, and Steve Chu, and his colleagues in Stanford, where he had moved. And guided by the new theory, now that we had an understanding of what was going on, we got down to temperatures below 1 microkelvin. We got cesium atoms, the ones that we want to use to make clocks. We got cesium atoms down to a temperature below 1 microkelvin. That was 200 times colder than what the theory said was possible. It's 100 million times colder than liquid nitrogen. And liquid nitrogen boils when it's poured out on the ground. Unless you've been in a low temperature physics laboratory, this is probably the coldest stuff you've ever seen. 77 degrees Kelvin. We're talking about something that is 100 million times colder than liquid nitrogen. It is 4 million times colder than outer space. And by the temperature of outer space, I'm taking the microwave background temperature that John Mather has measured the hell out of and found out I won't, he'll tell you all about that, about how the amazing things that he's done with measuring that background temperature. But that's, a little bit below 3 degrees. We're talking about something that is 4 million times colder than the coldest natural temperature in the universe. The thermal velocity of these atoms, instead of being a couple hundred meters per second, is less than 1 centimeter per second. When you've got atoms going that slowly, you should be able to make an amazing clock. And indeed, our colleagues out in Boulder have made such amazing clocks. This is Don Meekhoff and Steve Jeffers, and they laser cool atoms below 1 microkelvin here. They toss them up in a vacuum. They come back down, and you see what happens. If you toss something up in a vacuum, about a meter, instead of having a meter long, you have a meter up, and it comes back down after about a second. So instead of a few thousandths of a second, you get a whole second to look at the atoms. They're only moving at a couple of meters per second instead of a couple hundred meters per second. And as a result, these atomic clocks are the best primary frequency standards ever made. We call them fountain clocks because it's sort of like this water fountain that goes up and comes back down. But these things are now good to about a part in 10 to the 16, about a factor of 100 improvement over the old ones. That means 1 second in 300 million years. But you know what? You might ask, what if you want to keep it in a bottle? What if you want to keep it someplace? Where do you keep the coldest stuff in the universe? Let's imagine that this salad bowl is the container in which you want to keep your atoms. If the salad bowl is hot, then that means that the molecules in the walls of the salad bowl are moving around really fast, and they're going to heat up the atom, and you won't have a cold atom anymore. On the other hand, if the salad bowl were cold, if the bottle were cold, it would just stick the way things did with the, let's go to the document, the formula. So that means if you want to hold on to something, then you're going to have to hold on to it without having a bottle that's made out of material walls. And the answer, at least one of the answers, is magnetism. Because I'm sure that when you were young and you played with magnets, you found out that you could push one magnet around with another one without touching. Remember the first time you did that? Isn't that amazing? I'm still amazed by that. And so we can push on one magnet by with another magnet without touching it. Now let's go to the other camera, and that's what we're going to do with our atoms. So first I'm going to show you a kind of a toy version of this. If you had enough magnets when you were a little kid, you might have tried to make one of the magnets float above the other magnets by laying them out on a table or something. And that's what I'm going to try here. So here's a big magnet, and it's pushing up on this little magnet. The little magnet represents our atoms, the things we want to hold. The big magnet represents what we call our trap. And the big magnet's pushing up on the little magnet, and right here, the forces are balanced, and if I let go of the little magnet, it should just float. And when I let go of it, it doesn't do that. It flips over and gets pulled down. And that's what always happens when you try to do this with ordinary magnets. But you learn something else when you were a kid, and that is that if you spin a top, that it won't fall over. And it turns out our atoms are actually like little tiny spinning magnets, so when we spin it and take it up to the place where the force balance is, then but any two-bit magician can levitate a woman and then pass it, carefully avoiding the wires that are holding her up. You've never seen a magician do that. You see, this is a real deal. So let's go back to the laptop now. So that's the toy version of a magnetic trap. So now what we're going to do is we're going to see the real thing. This is a video of real trapped atoms. Okay, so what we have here is a cloud of cesium atoms. It's about 2 millimeters across at a temperature of about a microdegree above absolute zero. It's been released into the trap, bouncing back and forth a little bit, and as time goes on, it disappears because the vacuum isn't perfect. But over time, we learn how to make better vacuums. Now we keep these things for more than a minute instead of just a few seconds. And so using magnetic and other kinds of traps, we can now hold atoms for many seconds, and often the amount of time is only limited by the quality of the vacuum. And so we can do things. I haven't explained what an optical lattice is, but it's using laser beams to suspend the atoms. An ion trap is using a combination of electric fields and sometimes magnetic fields to suspend the atoms. And using these kinds of techniques, out in our labs in Boulder, Junyi trapping thousands of laser-cooled strontium atoms and looking at a ticking frequency that is in the optical on the order of a few times 10 to the 14 or 10 to the 15 cycles per second, has made a clock that is good to 2 parts in 10 to the 18. But we're not done yet. Dave Weinland, trapping single ions, has gotten down below a part in 10 to the 18th, 9 times 10 to the minus 19. My friends, that is less than 1 second in the age of the universe. The National Institute of Standards and Technology, an agency of the United States government, this is what we call close enough for government. And so we come to the end. The end of an odyssey of looking for colder and colder temperatures. And to illustrate that, I've shown this cartoon logarithmic formula where each tick mark is a factor of 10. So up here at the top, not the hottest temperature there is, but pretty hot, the surface of the sun, around 6,000 degrees above absolute zero. Room temperature, where we are now, just a little bit cooler. Liquid nitrogen is only a little bit cooler than that. And on this scale, even outer space is only a little bit cooler than the surface of the sun. Optical molasses, what Steve Chu measured back in 1985, is colder compared to the temperature of outer space. than outer space is compared to the surface of the sun. But that was just the beginning. Subdoppler cooling got even better. I haven't told you about Bose-Einstein condensation, but using these traps and using other cooling tricks, we've gotten down to temperatures below 500 picokelvin, below 1/2 of 1/1000th of a degree above absolute zero. And right now, there are experiments in the International Space Station where we're hoping that we will get the temperatures even colder, maybe on the order of a picokelvin or less. So what's next? Well, better clocks. The definition of the second is going to change because of those clocks. Those clocks are being used to make tests of our most fundamental theories of nature. We're using these cold atoms to do quantum simulation so we can understand insoluble mathematical models of the way many-body quantum systems behave. Quantum computers, I wish I had time to tell you about that. We're using cold atoms as quantum bits in quantum computers and more. And it may be that the young people here in this audience are going to be the ones who come up with the most exciting ideas. And if you continue in this business, then you may join a research group like this one, pictured a few years ago, where people from all over the world have come together to explore some of the mysteries of nature. And so we come to the end of the talk, but you know, it's not really the end because there's always something new to learn. Thanks very much.
Thank you, Bill. Are there any questions? We have time for one or two questions.
And if you ask a question, I'll give you a prize.
Here's a question.
Caroline, coming back to you.
There's one here.
Here. Oh.
Over in the back.
Would you run and give the prize to whoever represents me? The prize, by the way, is something that every physicist